Welcome to the Explainer. So today, we're going to tackle a principle that connects something as simple as your phone charger to the incredibly complex cells in your own body. It's all about the thermodynamics of irreversible processes. Now, I know that sounds like a mouthful, but trust me, by the end of this, it's all going to click. So let's start with a little puzzle. You take two wires, made of different metals, and you join their ends to make a loop. Then you heat up just one of those junctions, and something kind of magical happens. An electric current actually starts to flow. This thing is called a thermocouple, and it looks like it's making electricity right out of thin air. Or, well, heat. But how? How does that even work? Well, to get to the bottom of this, we have to step outside the neat and tidy world of classical thermodynamics. You see, the real world isn't perfect and unchanging. It's dynamic, it's messy, it's always in flux, and that's where all the interesting stuff really happens. Okay, so classical thermodynamics, you could almost call it thermostatics. It's great for describing systems that are in perfect equilibrium. You know, like a cup of coffee that's been sitting out so long it's the exact same temperature as the room. Nothing's changing. But it has a really hard time explaining a system in what we call a steady state. Think of a metal bar where you're heating one end. Heat is constantly flowing from the hot end to the cold end, so the temperature isn't uniform. But, and this is the important part, the temperature at any one spot on the bar stays the same over time. It's a dynamic situation, not a static one. And that right there is the key to our whole puzzle. The thermocouple isn't in equilibrium. It's in a steady state. There's a constant flow of heat energy coursing through it. And that means the old rulebook, well, it just doesn't quite apply here. We need a new way of thinking, a more powerful framework to really get what's going on. So, let's learn the language of this dynamic world. It's called irreversible thermodynamics, and honestly, it all starts with two really simple ideas: forces and flows. You've actually seen this pattern all over the place, even if you didn't realize it. Lots of basic physical laws follow this really simple pattern. You have a force, like a difference in temperature, and it causes a flow, like, you guessed it, a flow of heat. It's the same thing with electricity. A difference in electrical potential, that's the force, drives an electric current. That's the flow. It's this super intuitive cause and effect relationship that shows up everywhere. And we can boil all of this down to a beautifully simple formula. J equals L times X. The flow is just proportional to the force. And that L in the middle, that's just a coefficient that tells you something about the material it's flowing through, like how well it conducts heat or electricity. Simple, right? Okay, but here's where it gets really interesting. In the real world, these things almost never happen in isolation. A flow of heat can actually mess with a flow of electricity. A flow of some chemical can affect the temperature. This interference, this mixing of effects, has a name. It's called coupling. So when these processes are coupled, our neat little equation gets a bit of an upgrade. Look at these equations here. They show that the flow of heat isn't just caused by a temperature difference anymore. Nope, it can also be influenced by an electrical force. And, at the same time, the flow of electricity can be pushed or pulled by a thermal force. Those terms, L12 and L21, are the real magic here. They're the cross-coupling coefficients, and they measure exactly how much these two processes get in each other's way. For a long time, scientists saw these weird coupled effects, but they were just observations. There was no deep theory behind them. Then, in 1931, a physicist named Lars Onsager came along and had this incredibly profound insight that revealed a hidden, beautiful order underneath all this complexity. He asked what seemed like a really simple question. Is there some kind of fundamental connection between these cross-coupling effects? That L12 number that tells you how much heat affects electricity, is it related in any way to the L21 number that tells you how much electricity affects heat? And the answer? Well, the answer turned out to be breathtakingly elegant. Yes, they are related. In fact, they are identical. They're exactly the same. This is Onsager's reciprocal relation, and it's basically a cornerstone of all of modern thermodynamics. So here's the crucial point, what this all means. The universe has this deep, hidden symmetry baked right into its code. The way a temperature gradient can create an electric current is precisely the same as the way an electrical current can create a heat flow. It's a perfect two-way street. All right, so now that we're armed with this powerful idea of symmetry, let's go all the way back to our original mystery. We can finally build a complete picture of that thermocouple and make sense of everything that's happening inside those two little wires. First step is the Seebeck effect. This is the main thing we saw at the beginning. You have a temperature difference, that's our thermal force, and it creates a voltage, which drives our electric current. This is the thermometer part of the thermocouple. Then you've got the flip side of that coin, the Peltier effect. This is the reverse. Here, we're the ones driving an electric current, our electrical force, through the junction. And what happens? It actually causes a flow of heat. It can either heat up or cool down that junction. This is how some of those tiny portable coolers work. And then there's one more kind of subtle piece to this puzzle that happens along the length of each individual wire. It's called the Thomson effect. It basically says that a wire will either absorb or release a little bit of heat as a current flows through it from a hot area to a cold area. And this is where it all clicks into place. This is Onsager's genius. Before he came along, these three effects, Seebeck, Peltier, and Thomson, they just seemed like three separate, quirky facts about electricity and heat. But Onsager's reciprocal relation proved they weren't separate at all. They are three sides of the very same coin. They are all just different results of that one deep, symmetric coupling between heat and electricity. But the importance of this deep symmetry goes way, way beyond thermocouples. This is a fundamental principle that applies to countless systems that aren't in that perfect, boring state of equilibrium. I mean, this principle of symmetric coupling is absolutely everywhere. It explains how a change in temperature can actually separate a mixture of gases. It describes how different chemical reactions can speed up or slow down each other. And get this, it's at the very heart of biology, governing the complex dance of energy and matter that has to happen across the membranes of every single living cell, including yours. It's happening inside you right now. So what's the big picture here? The big takeaway? It's this. Our universe is constantly changing, constantly producing entropy through these irreversible processes, but it is not just random chaos. Onsager's relation shows us there's this beautiful, hidden symmetry that governs the very nature of that change. It proves there's a deep, profound order within the flow. And that leaves us with one last, fascinating question to think about. We live in a universe that is defined by constant, irreversible change. It's a universe where entropy always increases, which gives us what we call the arrow of time. So if a fundamental symmetry like this one lies at the very heart of all that change, what other incredible secrets about the nature of time and of reality itself might it be just waiting to reveal?